All right, so yesterday we started talking about all the different classifications of matter. Said we can have pure types of matter that can either be elements, meaning they're one thing from the periodic table, or compounds or molecules, which is more than one element bonded together. Or we can have matter that's a mixture. It could be either homogeneous, meaning evenly mixed, or heterogeneous, meaning different throughout. I did want to kind of come back to the compound versus molecule thing, because that does confuse people. And we'll try to define the difference between them. It's a subtle difference and not a very important one, but it's just more of a definition one. So a compound equals two or more different elements that are bonded together, where a molecule could be two or more elements of any type. And in fact, they can be the same. So if we think about something like oxygen, the oxygen we breathe is O2. Would that be a compound or a molecule or an element? It would be a molecule, right? So O2, two oxygen atoms, they're the same type, so it would be a molecule. If we're referring to one oxygen atom by itself, we would say that's an element. But because we have more than one together, we call it a molecule. It's kind of a semantic thing, but try to use the correct terminology. I occasionally even flip-flop them, so I'm not going to be a huge stickler, though. All right, so let's take a step back and look at elements a bit more. And like I said, you can find elements on the periodic table, and they're the fundamental building blocks of matter. It's pretty easy to remember that. They're, as one student said, they're like the Lego pieces that build things. Okay, so if we think about an element is going to be just one thing from the periodic table. So for example, we said yesterday you could have a bunch of helium atoms floating around, and we like to use the symbols rather than writing out the full name. So a helium balloon could just be a bunch of helium atoms floating around in space. A compound or a molecule is a bit different. And yesterday we went over the example of water, and we said water is always going to be two hydrogens that are bonded to one oxygen. So this would be a water molecule, this would be a second water molecule, and we could draw a third in for good measure. But the key difference here between an element and a compound is a compound always has a fixed ratio of bonded atoms, not individual atoms. So in this example, we always have two hydrogens for every one oxygen. If we change that ratio, like we talked about yesterday, and we add in a second oxygen, we'd be making hydrogen peroxide. We have to be very careful with the ratio. In addition, it's really, really hard to rip apart these bonds, so they don't do that very readily. All right, so we already took a look at some of the elements versus molecules example, but just be careful. Anytime you see more than one element in some sort of combination, it's going to be a compound or a molecule versus by itself, it'll be an element. Make sense? All right, so now we got to get into measurement, which you practiced a little bit yesterday in lab. And measurement is really important in science, and scientists often use a special measurement system, and it's called SI units. And I don't speak French, but I'll do my best to spell this out. Whoops, I think I got the accent on the wrong E. So they use SI units. Essentially, these units were developed in France. There was a problem for a long time where every country was using slightly different units for measuring things. We still do as Americans today, right? Like we measure things in pounds where the rest of the world doesn't. However, quite a while ago, they got together and they said, this is creating a huge problem. We need to have some sort of standard system that scientists throughout the world use. And that's where SI units come from. In fact, in France, they actually have the standards located under lock and key. You can go to France and actually see the kilogram standard, for example, or the meter standard. Hi. Are you here for the WTC? Yeah, come on in. Sorry, we'll pause here for a second. All right, so we said that international scientists got together and they said we need to have some sort of standardized system for measuring things in science. And let's make a list of physical properties. We'll have the SI unit over here that they use to measure it, and then we'll do the SI symbol over here. Okay, so a couple days ago we went over physical properties. We said you can measure something's length. How do we measure length internationally? Not in the US, so not yards, not inches, meters, absolutely. So internationally, we measure things in meters. And the symbol for meters is easy to remember. It's lowercase m. All right, we can also measure things by mass, right? What's the international system for measuring mass? It's not pounds. Grams or kilograms, right? The SI unit for physics is usually kilograms. I'm going to put a little asterisk here because chemists oftentimes don't use that kilo part. They just measure things in grams. Like you did in lab yesterday, you measured the mass of pennies in grams. The SI unit is going to be lowercase k, lowercase g for kilograms. All right, for volume, does anybody know the international SI unit for volume? It's not quarts. What was that? Close, not quite. Think about a Nalgene bottle. Nalgene bottle is about a liter, right? So liters are used internationally. If you go up to Canada and purchase gas, it's all in liters, right? So liter is the international measurement for volume, and it's going to be a capital L for liter. Temperature can be measured with international units. This one's a little bit less intuitive. If you go to Canada, what do they measure temperature units in? Celsius, right? They don't use Fahrenheit in Canada. However, chemists and physicists even go one step further and they use a system called Kelvin. If you go on and ever take a physics class, you'll cover this in more detail. But an easy thing to remember is if you do Celsius, so degrees Celsius plus about 273, that will equal that same value in Kelvin. Does anybody know why physicists like using Kelvin? It's a little bit weird. They have this thing called absolute zero. So if you cool something down as cold as it can possibly get, you'll reach a point where you can't cool it down anymore, and they define that as zero. So it's just a standard unit in physics. Did you have a question over there?
You asked if, does anybody know why?
Oh, okay, sorry. So the unit for Kelvin is going to be capital K. However, just like with kilograms, chemists often don't measure things in Kelvin. They just use Celsius. It's easier for us to do that. So sometimes there's disagreement depending on the field that you're in. Time is a lot easier. We measure things in seconds. The symbol for seconds is just going to be S. It's nice and easy. If you go on and take physics, you might discuss something like current. And currents, we measure in amp. We're not going to really use this very much, but you might see it in other science classes. But you, for example, for most household plugs, there's about 15 amps of current in there. Amps are the things that kill you. That's something people don't realize. People think voltage will kill you. Voltage doesn't really matter. Amps are the things you got to worry about. I think it's around 100 amps will kill you like right away. However, you could touch a 1,000,000-volt line and probably survive. It just depends on the situation. All right, and then we've got luminous intensity. That's basically how bright something is. So like a light bulb could be measured that way. And the unit for this is candela. And it's lowercase c, lowercase d for the symbol. So we won't use it very much, but you might see that in other classes. And then the big one that we do use is a system used for counting the amount of something that you have. And this is called a mole. We'll spend a lot of time talking about moles later. And the symbol for mole is MOL. Chemists, when they count molecules, it's going to be an extraordinarily large number, so they created a system. The way I like describing a mole is it's kind of like a baker using dozen. It's just easier to count large amounts of things. All right, and I did want to add an asterisk here because we saw in lab yesterday that you didn't measure things in liters. What did you measure the volume of pennies in? Milliliters. So I did want to include kind of a note that chemists oftentimes vary a little bit. They often use grams rather than kilograms. They often use milliliters instead of liters. And they often use Celsius rather than Kelvin. It just kind of depends whether or not you're doing more chemistry or more physics. All right. It is kind of tricky being a chemist, though, because oftentimes you're measuring really, really tiny things or really, really large things. So scientists often use prefixes when measuring very large or small things. So I'll give you an example of one. There was an experiment done, I think it was the 1600s, called the Cavendish experiment, where they're actually able to determine the mass of the Earth. Pretty interesting stuff. We're not going to talk about it too much. But what they did was basically they had pendulums and they could kind of determine how far they were swaying, and that's influenced by gravity, and gravity is influenced by mass. All right, so what they did was they determined the mass, and it came out to about this number. Let me do a count here. 1, 2, 3, 4, 5, 6, 7, 8. All right, so this is the mass of our planet, give or take a few grams, right? All right, this is a pain to draw. It's a lot of zeros. And you can imagine you have this decimal point over here. A simple thing you can do as a scientist, so you just grab this decimal point and you move it all the way behind the first non-zero digit. So how many places did we move this? You can go up and we can count, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27 places over, right? So what we'll do is rewrite this, and we'll say, all right, if we move that decimal point 27 places over, that would be now 5.97 times 10 to the 27th grams. And really, all this means is that we moved the decimal 27 places to the left. All right, what do you think happens if we move the decimal to the right? It might be a negative number, right? And we'll see examples of that later on. But this is called scientific notation. That's when you have an exponent, so it's 10 raised to some power, and all you need to do is move decimal points to figure out what that exponent should be. So that's pretty easy. Let's just make a note. This is called scientific notation. It's just a lot easier to write out. It's a lot easier on the eyes. All right, let's do a slightly different one. This time we're going to measure the mass of one hydrogen atom. And you can go ahead and do this one too. Let's see. I think that's right. Let me double check. I've got 3, 12, 15, 18, 21. All right. I think I've got this right, but I'll correct it if I don't. What we're going to do this time is we're going to move this now behind the first non-zero number, and then we can count the number of spots that we moved it. So we're going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 spots over. Okay, so we can write this out now as 1.67 times 10 to the what? Yeah, negative 24 this time because we're moving to the right. And I forgot to include my units here, but this would be in grams. This is a lot easier than writing out all those zeros, otherwise it's easy to miscount. Does that make sense? If you type this into your calculator, for example, and hit equals, the calculator will probably say that's too many zeros and re-spit it out this way. Sometimes in your calculator, instead of showing the 10, it'll just say E. How many of you have seen that E symbol? E is just shorthand for 10 raised to some power. So anytime you see that in your calculator, just think of scientific notation. All right. Occasionally, instead of scientific notation, we'll use prefixes. And so we'll take a look at a few examples of this. So prefixes are also used for large or small numbers. So you can use scientific notation if you want, or you can use a prefix, and I'll show you an example of this. My favorite example to use is Batman, if you're a DC person. Batman has a mass of 95,000 grams, give or take. Right? All right, so first we'll do this in scientific notation. How would we represent Batman's mass using scientific notation? And remember, we could imagine there being a decimal there. What did we do? Yeah, so what we could do is move this decimal point, over 4 spots after the first non-zero number. So this would be now 9.5 times 10 to the 4th grams. That's scientific notation, which we just practiced. Or you can do this with prefixes. And this would be 95 kilograms. Essentially, the prefix kilo stands for 1,000, or 10 to the 3rd. Same thing, right? So really, if you take 9.5 and multiply it by 10 to the 4th, it's going to be the same thing as 95 times 1,000. It gives you the exact same number out. It depends on the circumstance, and in this class, we should be comfortable doing it both ways, right? Does that make sense? The prefixes are a little tricky. You are lucky. This is the first year where you get a cheat sheet for exams and quizzes, and you don't have to memorize all of them. So how many of you have the handout that I gave you up front? If not, pull that out. All right, so during exams and quizzes, you'll have access to this. I'll give you a copy, but you should know how to use it, right? This is just a tool. And what I like to do is down the middle, you can kind of draw a line going along here. Basically, everything above that line, you can tell, is larger than the base unit. Everything below is going to be small, and it's pretty complicated. That's why I'm not forcing you to memorize it. The first prefix is an absolutely massive number, tera. Where do you often hear tera? Terabyte. Like if you buy a laptop or a phone, it'll measure the memory in terabytes. That means it's 10 to the 12th bytes. A byte is a unit of information that's stored in a computer. Same thing with giga. You might have a phone with, let's say, 16 gigabytes in it. That means that you've got 10 to the 9th bytes. Going down, same thing usually seen in computers. Megabyte, that's a smaller file size. That would be 10 to the 6th bytes. You go down lower, we've got kilo, like we just saw with Batman. Kilo is 10 to the 3rd. Hecto isn't commonly used. Does anybody know where this is mostly used? Yeah, land measurement. So hectacres, that's what's commonly used internationally rather than acres. We don't really use it very often in chemistry, so we probably won't see very many examples of this. Deca is also one that's not used very commonly in chemistry, but that's 10 to the 1 or just 10 if you want to describe it that way. All right, so these are all large numbers. If we go down, we've got deci. Deci is not very commonly used. Centi is, right? So centimeters, you're probably familiar with. That's 10 to the negative 2. Milli, a millimeter is 10 to the negative 3 meters. Micro has this funky symbol. So make sure that you don't draw a U. You actually need a tail coming off the front as well. That's 10 to the negative 6. Nano is 10 to the negative 9th. Pico is sometimes used in chemistry. It's 10 to the negative 12th. And femto is 10 to the negative 15. I do want to kind of put stars next to the ones that are most common in chemistry. So kilo is really common. Centi is really common. Micro is really common. Milli is common. And micro is really common. So those are kind of the 4 big ones that we run into over and over and over again in chemistry. The other ones you might see, you might not. They just aren't as commonly used. We also on the sheet have a bunch of other useful conversions. So let's say you're in your kitchen and you want to convert pounds to grams, you can use these conversions. And we'll practice conversions later on. Does that make sense? And then down here we've got polyatomic ions. Don't worry about that now, that's just for later exams. All right, let's do a little bit of practice. All right, so let's take a look at nanometers. A nanometer can be described as 10 to the negative ninth, right? So 10 to the negative ninth could be used to describe this. So you could say it's 10 to the negative ninth meters equals 1 nanometer. So that's one way of writing it. Another way of writing this, it's kind of confusing, but you could say 10 to the ninth nanometers equals 1 meter. It's the same thing, right? Basically all I'm doing is a mathematical operation, but these two ways of writing it are equally valid. Or you can say 1 nanometer over 10 to the negative ninth meters is equal to 1, right? That's basically just saying this divided by that is equal to 1, or that divided by that is equal to 1. So you can use that. Or you can say 1 meter is 10 to the ninth nanometers equals 1. So there's a million different ways you can write these equivalencies. I shouldn't say a million. There's like 6. But we'll use these eventually when we start doing unit conversions. So it is really important to know how to use that sheet. Oftentimes what students do is they'll memorize some sort of base number and then go from there. But we'll do a lot of practice. So let's practice with a few right now. So the first one is, let's replace with a prefix. So we've got 8.01 times 10 to the negative 6 grams. That's our first one. Then we'll do 1.05 times 10 to the negative 3 meters. And then the last one we'll do 7.9 times 10 to the negative 3 liters. All right, so the first one, what is 10 to the negative 6? What prefix can we use? Micro. So this is the one that has that funky U shape. So we can go ahead and we can say this is the same thing as 8.01 micrograms. Not too bad. All right, what's 10 to the negative 3? Milli. So it's small m, not big M. That's one important thing to remember. What's big M? Mega. So that's a completely different unit. We have to be very careful with capitalization. So we'll go ahead and say this is the same thing as 1.05 millimeters. Same thing down here, 10 to the negative 3 would be lowercase m. So now we could say this is 7.9 milliliters. So you can easily convert between these back and forth pretty quickly. All right, now let's try a harder one. We'll do the opposite direction. Okay, so I'll give you a few examples for this one. We'll do 45 milligrams, so mg. And instead of having it be in milligrams, I want you to figure out what it would be in grams. Then the next one, we'll do 125 nanoseconds, and we'll do that to seconds. And then last but not least, we'll do 10.7 microliters, and then we'll convert that to liters. So I'll walk you through the first one because it is a little bit tricky. But let's replace this milli unit, and what does that stand for again? 10 to the negative 3 on that cheat sheet. Okay, so now what we can do is we can say, okay, this is the same thing as 45 times 10 to the negative 3 grams. However, there's this weird thing with scientific notation where you always want the decimal after the first non-zero number, right? So imagine that you've got this decimal over here. Let me make it red, actually. and we're going to move it over to the left one spot. When we move it to the left, does the power of 10 go more positive or more negative? More positive. So what will our new number be? It'll still be 4.5, but it'll be 10 to the what now? -2, absolutely. So this would be proper scientific notation for that, but if it helps to break it down into steps like this, go ahead and do it. The easiest thing you can do to double check your work, plug this into your calculator, write down your answer, plug this into your calculator, it should give you the same answer, right? So you can always double check your work that way. All right, next one, we've got nano, which is 10 to the -9 if you look at your cheat sheet. So this would be 125 times 10 to the -9 seconds. Are we done? No. Just like before, we've got this decimal point that this time we're going to move 2 spots over. So this would now be 1.25 times 10 to the what? -7. We're going more positive because we're going to the left. And again, if you ever get stuck or just simply confused, just put both into your calculator and double check. All right, one last one. Micro is 10 to the -6. So we can go through and we can say, all right, this is 10.7 times 10 to the -6 liters. Just like before, we're going to move this decimal point 1 spot to the left because we want it to be after the first non-zero number. And now this would be 1.07 times 10 to the negative what? -5. And there you go. So it is important to know how to go back and forth with these to go from, let's say, this number to a prefix or vice versa. Yep.
Would the second one be S?
Oh yeah, that should be S, excuse me. Good catch. This should be seconds. All right, so when you're doing this, just make sure you go slow, double check your work on your calculator. If it helps to use scratch paper, use scratch paper. It's really easy to get things flip-flopped, especially when you're going back and forth. All right, let's do some estimation. I always like to have some sort of generic day-to-day item we can estimate standard things with. So for example, 1 liter is about the volume of a Nalgene water bottle. Does everybody know what a Nalgene water bottle is? It's one of the big hard plastic water bottles that you might take backpacking. Alternatively, it's about 2 standard size regular water bottles that you might buy at like a vending machine. So I'll just write volume of a Nalgene. 1 meter, some people will say is about a yard. The other thing I like to do is extend your hand out. It's about how far away your finger is. Granted, if you're LeBron James or somebody, it might be a little different, but it's roughly that. So we can use that as an estimating tool. One kilogram is about the weight of a full Nalgene. So if you ever have one of those full Nalgenes full of water, it's going to be about 1 kilogram. It's about 2.2 pounds, if that gives you any reference. And then 1 gram, I tell people, is about the mass of a paper clip. It's important to have generic ideas of how big or small these things are in your day-to-day life. That way, if somebody says, oh, how far is it across the room? And you said 10,000 kilometers, they'd be like, no, that's not even close. If I were to estimate how far it is from me to that wall, what would be a reasonable estimate in meters? Yeah, we could even go, 1, 2, 3, 4, 5, maybe 5 to 6 meters. So you can use steps, things like that. But scientists like being able to estimate things on the fly so we can get quick measurements. Does that make sense? Okay, so the last thing we're going to do is practice measuring things in the lab, which you kind of did yesterday. However, I'm going to give you some guidelines for this worksheet, and it kind of feeds into the problem of the day. Step 1 is determine the units for the smallest hash mark. Oh, that's not mark. And step 2 is estimate one digit past that. All right, so let's take a look at the first one. What do the hash marks represent on this ruler? Are they the tenths place, the ones place, the hundredths place? What do you think? Looks to me like a ones place, right? Pretty simple. We're going 10, 11, 12, 13, 14, 15. So each of the hash marks represents a ones digit, right? So this would be 11, 12, 13, 14, 15, and so on. So we know for sure that that blue line is somewhere between 15 and 16, right? What this means is that as a chemist, we need to estimate the digit past the ones place. So we want to estimate down to the tenths place, right? So what would we say this would be? Does anybody want to throw out an estimate? 15.9? Sure, let's write that down. 15.9, and the units are centimeters. And the way I like to break this down for students is this is certain, right? Whoop. We are 100% confident that that blue line is in between 15 and 16. It's definitely not below 15. 100% positive there. All right, and then after that, we could say, all right, this portion of the line, the tenths place, we estimated that, and that's always going to be our last digit. Would it make sense to ever write 15.9253? No, you'd be estimating stuff that just simply doesn't even matter. We only estimate one digit beyond what we're certain with. All right, what about this next one? We've got smaller hash marks now. Those look like the smaller hash marks between 15 and 16. Now go to the tenths place, right? There's 10 hash marks there. So what would the correct measurement for this be? Okay, so you said 15.8 is certain. So we can see absolutely this is between 15.8 and 15.9, right? That's 100% confident. But then we want to estimate one digit further, and somebody said 5. Sure, let's do that then. So 15.85 centimeters. Just like I said before, this first set of numbers is certain. And this last number, the 5, was just estimated. You don't have to be 100% right when you're estimating something. You just want it to be roughly correct, right? All right, what I'm going to do is give you a few minutes to work on 3 and 4, and then check with your neighbor. All right, give me a thumbs up if you're confident on 3 and 4. A few people? All right, so let's start with 3. When I look at this, the smallest hash marks aren't single digits like ones place, right? Because we can see we've got hash marks in between those ones places. So this would be a 10th place certainty, right? Okay, so when I look at this, it's definitely after 15.3, I would say. Does everyone agree? So that's 100% confident. That'd be 15.3. I'm going to underline this as green for certain. And then we want to estimate one digit further. So anybody want to throw out a number? What do you think? 2. Okay, so 15.32 centimeters. Like I said before, this last 2 is always going to be estimated. This is important, and we'll talk more about this later, but it falls into a classification known as significant figures, and it's important to show all of your significant figures. All right, last one, we've got, I would say 15.5 is pretty certain. And to me, it looks like it's just about on that line, so you can have 15.50, right? However, you do want to include that 0, because if you don't have that 0, it implies that you're just guessing that it's somewhere between 15 and 16, but we know it's really close to 15.5, so we'll write 15.50 centimeters. All right, that's where we'll stop today. When we come back tomorrow, we'll go over the problem of the day and do some of these more unique examples on the bottom.